Okay, so yesterday we were talking about average velocity, and I warned you I wasn't going to be here today, but we're still doing notes. If your class didn't do the previous page, if we didn't get to the end of the notes, that's fine. It's not a huge deal. We're just going to pick up from here, okay? So, use your calculator to generate a graph of x squared minus 4 divided by x minus 2 for x not equal to 2. Okay? So with your graphing calculators that I know all of you brought, go ahead and graph that function. Okay? I'll give you a minute to graph it. Okay, that's close enough to a minute. Remember, since this is a video, you can pause, rewind, fast forward, kind of jump around if need be. I'll also put this in Drive in case you need to see it. Okay? So, hopefully you've graphed it. I think if you graph it, you end up with something, let's see, that looks kind of like that. Okay, something approximately like that. If you didn't get that, that's okay. Make sure when you type it in, you're using those parentheses around the top and the bottom. Okay. So let's see what we get. I am using a new app, so kind of bear with me because I'm still trying to figure parts of it out. Okay. Whoops. See, like it's not the same as Notability, so it's going to take me a minute. Okay. So we got the graph. It kind of looked like a line, but that doesn't make entirely sense because we kind of got the squared on top. So why is it that x cannot equal 2? If I look back at my function, okay, why is it that x cannot equal 2? And x can't equal 2 because if you plug it in, 2 squared minus 4 over 2 minus 2. If you plug that 2 in for the x, we're going to get 4 minus 4 on top over 2 minus 2, which is 0 over 0, and that just doesn't work out. Okay, so it's undefined at x equal 2. But what's really going on, what happens at x equals 2? So at x equals 2, okay, what's going on? Well, let's think about this function. X squared minus 4 over x minus 2. Okay, let's think about this function for a second. Can we factor it? Can we factor the top? I think we can. And the bottom stays the same. So let's just factor the top. That's just a difference of squares, x plus 2, x minus 2. Okay. Hopefully you see that the top and bottom cancel out. Okay, so all we're left with is x plus 2. And that's a line. Okay, that's a line, but at 2, the function doesn't exist. At 2. So we have a line, okay, with a y-intercept of 2. 2 would be 4. And so what we end up with is something that looks like this. There's a hole there. Everywhere around 2, the graph exists, except at 2 specifically. Okay? Alright. So complete the table of values below to determine what happens as x gets close to 2. So as we approach 2 from the left. So here's what I'm going to do. I'm going to make y1, y sub 1 in my calculator, x squared minus 4 over x plus 2. No, wait, it's x minus 2, isn't it? Okay, so that's y1. Remember what I taught you yesterday? You press alpha. Let's try that again. Okay, so we're going to press alpha, trace, y sub 1, press enter, and then y1, and plug in your number, and that will get me my value. And we're going to do that until we get as close as we can to 2. Okay? Okay, so you should type that in your calculator. And we're going to do alpha trace. Yes, I'm doing this on my calculator with you. Y1 and type in 1.5 and we get 3.5. Okay, let's use a different color. Second enter will recall what I just typed in and I change it to 1.75. And I get 3.75. Okay. We do 1.9. We get 3.9. We do 1.99. We get 3.99. Maybe. Whoops. I don't know what you guys are seeing, but I'm tapping on stuff I probably shouldn't be. Okay, so I got 3.99. I do it again for 1.999. And the last there. Okay. Got a little bit of a lag. 3.999. Whoops. Okay. So 3.999 on that side. At 2, okay, we don't have a value because if we plug it in, it blows up because we can't divide by 2. So let's go from the other direction now. Okay. So let's go from the other... Whoa, I don't know what just happened. Let's go from the other direction now. Nope. Okay. Nope. Nope. I don't know what's going on. Okay, so I don't know what just happened. But this one, we should have a 3.999 there. Okay. Sorry, folks. Still trying to figure some of this app out. Okay. So now we slide over. And we're going to go... Whoops. We're going to go from 2.5 and we're going to come towards the 2. So let's see what we get when we plug in 2. So alpha trace Y1, enter. Parenthesis 2.5, we get 4.5. Okay, 4.5. We press second enter, we change it to 2.25. We get 4.25. Okay. Slide over, we got to try 2.1. So second enter 2.1 should get 4.1. And we do 2.01 and we get 4.01. Okay, then we do 2.001 and we get 4.0101. 1. Okay, so let's zoom back out for a second. Okay, so I'm sure you can make a guess as to what 2 should be. As x approaches 2 from the left, as x approaches 2 from the left, as x approaches 2 from the right, okay, I'm coming towards the same value. Okay, as I get closer and closer to 2, I'm getting extremely close . I'm getting extremely close from both sides. I'm within 10th, 100th, 1,000th. I'm within a thousandth. I'm within a thousandth of 2. Okay, so that's extremely close. And so I'm approaching 4. And that's the concept of a limit right there. Okay. Okay, so this is the concept of a limit. So as x approaches a value, what does the y approach? Okay, and the y is approaching 4. Okay, so definition of a limit. The limit of a function is the y value that the function approaches when the x value gets closer and closer to a point C from the left and the right sides. We then say that the limit of f of x as x approaches C is L, and we write the limit as x approaches C, f of x equals L. Okay? So what you're going to see, chances are when you're looking at problems like these, okay, you're going to find that this will be a number, the C will be a number, okay, C will be a number, and you're going to answer with a number, okay. So the limit as x approaches some number of some function is going to equal some number, okay, where this is a y value. Okay, so that's going to be a y value. That's what the function approaches. Okay. And notice what it says. It says from the left and the right. In order for this to happen, it needs to approach from the left and the right, from both sides. Okay? Let's take a look at example 7. Okay? Whoops. Example 7. Whoops, I'm sorry. Apply this definition to the function from above to find the limit as x goes to 2 of f of x. The limit as x approaches 2 of f of x. Okay, I forgot about part C here. I'm sorry. So we just found that. We just filled it in the table, I think, already, because you could probably see that in the table it was approaching 4. Okay, so the limit as x approaches 2 of f of x is equal to 4. Okay? All right. Let's take a look at example 7. Okay, use the graph to find the limit as x goes to 2 of g of x, where g is defined as the g of x is equal to 1 when x is not equal to 2, and 0 when x is equal to 2. Okay, so the first thing to do, the thing that would make sense first, is to graph it. So x is not equal to 2, that's going to equal 1. So, whoops, I'm sorry, I'm still using like the notability controls. Okay. So when x is not equal to 2, everywhere else it's equal to 1. When x is equal to 2, we're at 0. Okay? So use this graph to find the limit as x approaches 2 of g of x. Okay, so we need to find the limit as x approaches 2 of g of x. Okay, so as I approach 2 on the x-axis, as I come towards 2 on the left and right side along the x-axis, I trace my function. Okay, I'm tracing my function towards the value. Okay, so what y value does my function approach as I approach 2 on the x-axis? And I'm not talking where the function is defined. If you trace your pencil along the function towards 2, okay, so if I start on the outside and trace it towards 2, okay, where am I headed? If I come from the other direction and trace the function towards the x value of 2, I'm headed to a specific location. I have a specific value, and that value is 1. Okay? So the takeaway of this example is, what are we getting close to? We're getting close to 1, or we're getting close to 2. Let's say we're getting close to 2. I'm sorry. Not what it equals. Okay. We're getting as close as we can without touching. Okay, so and you know, actually we don't even need these arrows down here. Okay, if you don't even want to think about that, you don't have to. Okay, so we're tracing the function towards whatever x value I need to tend towards. So this function needs to tend towards 2, so I'm tracing the function towards 2 to see that the limit as x approaches 2 of g of x is equal to 1. So the takeaway of this example, okay, the takeaway message of this example is that the limit exists when the y value gets close to a specific point, even if that point isn't actually part of the graph. So in this example, 1 is not part of the graph at x equals 2, but that doesn't matter, okay, because we're tracing the function, okay? That's what you need to think of limits as tracing the function, okay? So I'm going to stop there because it's been 15 minutes, okay? Remember, you can rewind and rewatch if need be. Okay, so one-sided limits are next. Suppose we have the graph of f of x below. Notice the function above does not approach the same y value as the function below. Okay. So the function above does not approach the same y value as x approaches c from the left and right sides. This means that the limit as x approaches c does not exist, and we're going to come back to this in just a second. Okay. So as I trace my function this direction, I'm approaching a different value than if I come from that direction. Okay. Sometimes, however, we are only interested in what the function is approaching from the left or the right of c. And we can say this using the following notation. So the limit of f of x as x approaches c from the left is L, and the limit as x approaches c from the left is k. So the limit from the right and the limit from the left. And we denote these, I'm not sure if you've seen these before, okay, but we denote this with the plus sign for the right, okay, from the positive side, okay, and then we denote it with a minus sign for the left-hand side, okay. So thus, we can say that the limit of a function as x approaches any number c exists if and only if the limit as x approaches c from the right is equal to the limit as x approaches c from the left. And using limit notation, we have the limit as x approaches c of f of x exists if and only if the limit as x approaches c from the right of f of x is equal to the limit of f as x approaches c from the left of f of x. Okay? This is a key concept. Okay? And this is if and only if. Okay, so if they both don't equal the same thing, then that limit doesn't exist. Okay, no ands, ifs, or buts. Okay, so the limit needs to equal the same thing. Okay? So let's try an example. Number 8. Let f of x equal f minus 2x for x greater than 2 and 3x plus 1 for x less than or equal to 2. Oops, didn't mean to do that. So let's come over here and let's figure out what my starting point is. So I take the 2 and I plug it in. So 5 minus 2 times 2. 5 minus 4, which is 1. So for x greater than 2, I'm starting at a position of 1. I'm starting at 1. Oops, let's get my pen. And what's my slope? My slope is negative 2. And that's for x greater than 2. For x greater than 2, my slope is negative 2. So I come down 2 over 1, down 2 over 1. Zoom back out a little bit more. Down 2 over 1. Whoops. And I connect them. Okay. We got to do the other one now. We got to plug in 2 for this one. So 3 times 2 plus 1. 3 times 2 is 6. 6 plus 1 is 7. So it's up at 7 for x less than or equal to 2. So 2 is 7. 1, 2, 3, 4, 5, 6, 7. It's a closed circle, and my slope is 3. 1, 2, 3 over 1. 1, 2, 3 over 1. 1, 1, 2, 3 over 1. 1, 2, 3 over 1. Okay. Connect them. Whoops, that's not so hot. Okay. Alright. Whoops. So let's answer some of the questions. So we graphed it. Okay. Since there is a graph, we could probably assume that we would need to graph it. So let's find the limit as x approaches 2 from the right for f of x. So the limit as x approaches 2 from the right of f of x. So I'm tracing the function from the right. Trace the function towards 2 on the right hand side. So as I trace this function on the right side of 2, no, it's time out. As I trace the function towards an x value of 2, what y value do I approach? Well, the y value that I approach is 1. Okay. So, as I trace the function, I'm approaching a y value of 1 as x approaches 2. So over here I'm at an x value of 2, 3, 4, 5. X value of 5, 4, 3, 2. And what y value am I at? I'm at a y value of 1. Okay? Over here, the limit as x approaches 2 from the left. So as I approach 2 from the left, so I'm at negative 2, negative 1, 0, 1, and 2, what y value do I approach? I'm approaching a y value of 7. So what can we say about the limit as x approaches 2 of f of x? And the limit as x approaches 2 of f of x does not exist. DNE does not exist. And the reason it does not exist is because the limit as x approaches 2 from the right of f of x does not equal the limit as x approaches 2 from the left of f of x. Okay? Let me clean that up a little bit. Okay, so if they were approaching the same value, then it would exist. But since they don't, the limit does not exist. Okay? Okay. So there's that. Okay. So when do limits not exist? That's the next question. So when limits do not exist, if there does not exist a number L satisfying the condition in the definition, then we say the limit as x approaches c of f of x does not exist. So limits typically fail for 3 different reasons. 1, the function approaches a different number from the left and the right side. That's what we just talked about. The function increases or decreases without bound. Okay, as x approaches c. And lastly, it oscillates between 2 fixed values. So that's like your ADD function. Okay, so left and right, it approaches 2 different values. We've already seen that. Maybe it does something like this, and then something like that. Okay, so that's approaching 2 different values. What do I mean when I say it increases or decreases without bound? Okay, that means it's going to negative infinity, go to positive infinity. This is typically where you have vertical asymptotes. So your graph is like an exponential function where it's just increasing, okay? Just increasing without bound. Never stops. Okay? Lastly, the oscillating. These, like I already said, are your ADD functions. ADHD, ADD, whatever you want to call it. Okay, and the reason I say they're ADD functions, ADHD, is because oscillating, they're just going back and forth. So they're just going like this. Okay? And we're going to talk about those here in a second too. Okay. So let's investigate a few graphs, and we're going to use a graph and or table, and we're going to investigate the existence of the following limits. So first off, the limit as x goes to 0 of the absolute value of x divided by x. Okay. So what should we do? Let's graph it first. Okay, do you know what this graph looks like? If you plug in a negative number, any negative number, so let's just say negative number, divided by that same number, okay, it's going to be a negative number on top and a negative number on bottom. The absolute value of that negative number is just that number. On the bottom, you get a negative number. Okay, so a positive number divided by a negative number is negative 1. If you're not quite sure how I got that, try graphing it on your calculator. But you kind of have to think abstractly here, right? So if you take a negative number and plug it in the top, a negative number and plug it in the bottom, on top we end up with that number, but it's just positive, and on the bottom it remains that negative number. So on the graph, whoops, for any negative number, we're going to get negative 1. Okay, and we're not going to equal 0. Okay. What happens when we plug in a net positive number? So the absolute value of some positive number divided by some positive number. Absolute value of a positive number is positive. On the bottom we still have that positive number. So we just get 1. Okay. So this is just 1 going the other direction. Okay. So we could look at it graphically and say, okay, so I'm trace the function from this way, I get negative 1. I trace the function from this way, I get positive 1. Can't be both. So we have an issue there. We're going to talk about it in just a second. Let's fill in the table first. Okay, we could probably do that just by looking at the graph. Okay. So if we plug in negative 0.5, it's a negative number, you're going to get negative 1. If you plug in negative 0.25, you get negative 1. If you plug in negative 0.1, you're going to get negative 1. Basically, if you plug in any negative number, it doesn't matter which, you're going to get negative 1. Okay, we're going to come back to 0. If we plug in any positive number, we're going to get positive 1. Okay, doesn't matter which one we plug in, we're still going to get a positive number. Okay, so what can you tell me about this limit? Well, what can you tell me about this limit? The limit as x approaches 0 of the absolute value of x divided by x. Well, it doesn't exist. And why does it not exist? It does not exist because the limit as x approaches 0 from the right does not equal the limit as x approaches 0 from the left. Okay, because the left and the right limits are different. If it doesn't exist, you must give a reason. And it needs to be one of the 3 above. Okay? Remember, if you need to, you could always rewind it. Let's try graphing the next one. The limit as x goes to 1 of 1 over x minus 1 squared. Okay? Maybe I start by graphing it on my calculator. If you remember your basic functions, maybe you do, maybe you don't. 1 over x squared is a volcano function. Okay, the minus 1 on the inside shifts it to the right 1. Okay, So I come back over here to my graph. I have a vertical asymptote at 1. And it's going to shoot up. And it's going to come back down. Okay? So that's what the graph looks like. So this, the parent function, is 1 over x squared. And I went right 1. Okay, we need to figure out what happens as the limit as x approaches 1 of 1 over x minus 1 squared. Okay, so we did it graphically, we looked at it graphically, and we can start tracing it. Limit as x approaches 1. Okay, if we look at it from this direction, as I come closer to 1, I seem to be growing quickly. As I come from the other direction, I seem to be growing without bound as well. Let's fill in the table. Okay, so y1, I'm going to make 1 divided by 1 minus x squared. Okay, nope, just kidding. 1 divided by, 1 divided by x minus 1 squared. Okay. So I trace, and I'm going to figure out what 0 is. And I get 1. I do it with 0.5. I get 4. I do 0.9 and get 100. I do it with 0.99. I get 10,000. And I do it with 0.999, and I get, it looks like 1,000,000. 6 zeros. 1, 2, 3, 4, 5, 6. Yep, 6 zeros there. Okay, let's go on the other side. As I come to 2, okay, so alpha trace y1, 2. I get 1. I plug in 1.5, I get 4. 1.1, I get 100. 1.01, 10,000. 1.001, and it looks like I get 1,000,000 again. Okay? So what's happening as I approach 1? Does that limit exist? Okay? If you're not sure, look back up at the table above. Does it meet one of those 3 conditions? It does, because this one does not exist. Okay? Because, we've got to justify it, because the function grows without bound. Okay? The function's growing without bound, so it does not exist. Let's try one more. Try graphing this on your calculator, part C. So we're going to graph sine of 1 divided by x. Okay, let's go zoom standard. Okay, well that's not too bad. So first convince yourself that as you move to the right in the chart below, x is actually getting closer and closer to 0. So the top is staying the same, and the bottom is growing this time. Okay, so the numbers are getting smaller. Okay. Okay, so since it's 2 over pi, okay, that's really 2 over pi, 2 over 3 pi, 2 over 5 pi, 2 over 7 pi. Those are getting closer and closer to 0. Okay, so we're okay with that. So we're just going to try and plug in the values. So I already have sine of 1 over x in my calculator as y1. So I do alpha trace y1, and I do 2 divided by pi. And you should get 1. Okay. I do 2 over 3 pi, and I get, nope, 2 divided by 3 pi. Something isn't right. Okay, make sure when you're typing it in that 3 pi is in parentheses, because if it's not, you're not going to get the right answer. So alpha y1, 2 divided by 3 pi, you get negative 1. Do 5 pi, 2 over 5 pi, you get positive 1. 2 over 7 pi, negative 1. 2 over 9 pi, you get positive 1. 2 over 11 pi, you should get negative 1. 2 over 13 pi is positive 1. So as I'm getting closer and closer to 0, what value am I approaching? Do we know? Is it 1? Is it negative 1? Really, we have no idea. Because what's going on is I approach 0, y values are oscillating between 1 and negative 1. Okay? So this function keeps bouncing back and forth between 1 and negative 1 as it gets closer and closer to 0. So does this limit exist? And hopefully you see that this one does not exist. Okay, so the limit as x goes to 0 of the sine of 1 over x does not exist because it oscillates. Because, we'll just say the function oscillates. Okay? Alright, that's all we're going to do.